and they did also the vertical stripe. Ah, you did? Okay. Okay, so far, basically, for this general measure theory, let me just recall. Well, almost all the basic theorems are there. So we know, well, we know what is a sigma algebra. Then we have the outer measure. And whatever, and then we have the restriction to the measurable sets. So, and altogether they generate what is called a measure space, no? Which is the space X, the sigma algebra omega, and the measure. This is the triangle. Now, well, we have all the stuff as usual, and then we saw what are, well, yesterday, that the signed measures. So here I'm not adding what you have when you have for general measure space. We can be, well, the regularity, the limit theorem, so the monotone or Lebesgue or the Vitalik Theorem, whatever, everything works, just the change. And the regularity, the inner, outer regularity, if you are in a topological space, then okay, the Borel, in particular the Borel sigma algebra, in topological space or on metric space. Which is much better in metric spaces. So yesterday we saw sigma, the signed measure, the radionicodym. And then a simple tool to have to prove that essentially the measurable sets are the Borel set, which is the character-ordery condition. Okay, so today we conclude with the last, in my opinion, the last important result. So there is still one important result, and is that any finite measure on the Borel sigma algebra and metric spaces is sigma finite. So there exist counter-remaining compact sets such that the measure is contained in their union. And this is important because essentially it tells you that from the point of view of the measure, you cannot distinguish so a measure on a generic metric space with the Lebesgue measure is 0, 1, more or less. Okay. So what is left here is the way to compute the integrals for product measures. So yesterday we saw an example, no? The following example of the construction was the construction exactly of the product measure. So, and we did in RD, or well, in R2, let's say, and then you can generalize. So essentially you define the functional, so the outer measure on any set is the infimum of the sum of, let's say, the length of I times the length of Ji, where A is contained in the union of the interval I times Ji. And these are intervals. Okay, so we did a little bit more generally, but essentially let's stick with this example so I can use character-ordery condition. I don't need to do more complication. Okay, and then clearly the product is available on the topology. So if you have two sets which are disjoint, well, you can, which has a positive distance, you can always take the diameter of this set to be less than the half of the distance, so the coverings are disjoint. In that case, okay, the infimum is the sum, so they satisfy, so mu star satisfies character condition. And so this defines, well, the product measure, well, we still don't have yet, and then, yeah.
This definition, it's not, I mean, this formula, it's not equal to the product of the projections on the axis, no? For example, in R2, I take set in R2, and I take this set, I project it over the x-axis and the y-axis, and I take the two measures, the one-dimensional measures, and I take the product. Not correct.
So you say this set as this projection, this projection.
Yeah, and I take the product, but the measure, the one-dimensional measures.
Yeah, or this length times this length.
Yeah.
Then you get this larger square.
No, but it's measured.
You want to say if this is so instead of having this definition, I define the new measure, that is, I give you a set, I project, and then I take it.
Yeah.
Will not be added.
Well, it does not satisfy character condition for sure.
Yeah, it's not added.
So you can.
Yeah.
Hmm?
It's
You
not
can
added.
add the squares, which is not added to complete the big square. It will be the same.
Yes, the small is the same, and the largest are the same thing. So
Yeah.
I think, well, it is a function, but I wonder if you can build a measure. Because then you have to verify that it's subadditive, and I suppose so let's see if this is subadditive.
I guess it is because of the Cauchy-Schwarz inequality, no?
Yeah, this is subadditive. But then you have to define which are the measurable sets. And I think there are very few. But this is not the big measure in the play.
But I wanted to say that I noticed that if that was really concretely a measure, then the zero set for this is exactly the zero set of the other one.
The zero set for this one, for your measure,
Yes.
are not the zero set of this guy.
No, that's what I'm saying. I'm saying that for this measure that defined here,
Yes?
and for this one I said,
Yes?
they have the same negligible sets.
Are you sure? But the diagonal is negligible for the product, for the Lebesgue, but it's not negligible for the product, the projection.
Probably there is one diagonal.
So, okay, so mi star satisfy the character condition, and then, so mi star restricted to the Borel is a measure. Let's call it L2. So the Lebesgue into dimension is a measure. Well, so essentially we can integrate. Give me any, well, now it's clear, a Borel function, and then, well, I can also complete adding the sets of measure 0, which are defined at the one for which mi star is 0. I can compute, well, in theory I can compute the integrals, no? So then I have that, I can compute the integral, let's say for positive functions, or well, doesn't matter, x, y, let's call it dx dy. It's just a formalism, no? I know what is the measure, then this is computed by I take simple functions which approximate my f. I compute the integral for those simple functions, which is just a sum of. Well, I have some difficulty because I have always to compute what is the measure of a Borel set. But okay, suppose you can do. In any case, at the end, you need to compute L2 of any E for L. Okay, which is, well, you can compute it, use the formula. So what is left is if there is, well, you know, it's just a repeated integral, if there is a way to compute it without resorting to, actually for now what I know I have to do is, this formula, this estimate. I have to start with this guy, and then, okay, I pass to the limit in this guy. Okay? So, so now what is left is exactly product measures in general. So we cancel, and we restart with product measures. So in general, the general setting is that we have a measure x, a sigma algebra, let's say A. Now I need to distinguish, and then a measure B, and another space y, a sigma algebra B, and a measure N. And I want to define, well, like in this procedure more or less, what is the product measure. So define. Need to define on the space, the product space, some sigma algebra, and the measure which will be the product. Okay? Well, okay, we do the same. Let me see if we do exactly the same. So, set, but this formula here. Ni outer measure of any set, okay, let's call it, I call it A, is the infinite of the sum, well, okay, this is, I don't like it, let's call the set C. This is AI, mi BI, where C is contained in the union of AI times BI, and this set AI belongs to the first sigma algebra, and BI belongs to the second sigma algebra. Exactly the same. Okay. Well, now, since I don't have a topology, but I tell you, this almost never happens, because the measure theory outside metric spaces, it's very bad. So, if I don't have the topology, I need to prove in any case that the sigma algebra of measurable sets, so proposition, the sigma algebra of measurable sets contains the rectangles. Okay? So this is the restatement of being Borel in the case I don't have the topology, because when I have the topology, the product of two open sets is a base of the product topology, by definition. Okay, let's see if there is something interesting in this proof. Okay, the proof is. And I think yesterday I showed a comment about it. You remember? There was, so the proof, I just make the drawing, and then you understand. So essentially I take a rectangle, take a set C, and I want to prove that mi star C is equal to mi star, actually I need just this guy, C intersection the rectangle union plus mi star C minus the rectangle. This is the definition of being measurable. Okay, so what I do now? So in order to be larger, I take a covering here which is optimal, because from this infimum, so essentially if I take this which is optimal, and then I prove that from this covering I have two coverings of these two guys which are again, well, with two coverings and with the same measure, being the infimum, the real mi star is less or equal than my value. Okay, so let's take an so because well, this is the standard. If I have the infimum, I have to be careful which one should be the optimal one, and it is always the one which is above. Okay, so let's take a covering. That is not a very nice drawing, but now I think you remember that I did the drawing yesterday, no? What is left, it doesn't matter. Okay, how to make two disjoint coverings. So the advantage is that this rectangle, which is intersecting my R, can be divided into three rectangles, and the measure of their sum is equal to the measure of the larger rectangle. So essentially, if I take a rectangle here, so if
a question here has it's not the big measure. We are not sure that the separation is negligible.
yeah, but here I'm not asking that these sets are open.
Yes.
The trick is here. Bi, then, so I need to, what is Ri intersection? R is still a rectangle, so let's say is I prime times Bi prime, and Ri is equal to, okay, AI prime times Bi prime union AI prime times Bi minus Bi prime. This is just elementary stuff. I'm just rewriting these four sets. 1, 2, 3, 4. Time union Bi prime times, sorry, AI minus AI prime times Bi prime, and then I have the left, what is left, which is AI minus AI prime union Bi minus Bi prime. Okay. So essentially I'm saying that the drawing is messy, but if I have a rectangle and another rectangle, I take these four pieces and this sum over the four pieces is equal to the sum of the whole rectangle. Okay, so now what I do? For any covering of this guy, you divide it into these four pieces, and then you get a covering of this portion and the covering of the remaining part, which has the same measure, the same sum. The sum is the same because, well, the sum of the four is equal to the sum of the whole, is equal to the measure of the whole. So at the end I have from any covering of this guy, I build a covering of these two, which maybe is not optimal. So when I take the infimum, I get this inequality. Okay? So this is not going to be asked, but it's just for your knowledge. Okay.
At the end is the product.
Yeah, it's the product of what is left. Unfortunately, they put this thing here. So is A minus AI prime union bi minus bi prime. Okay,
Is the union of the product?
Times. So essentially, I'm saying that this is the first part. This is this part here. This is this part here, and this is this part there. Just this one. Okay. Very well. So rectangle are measurable, and their measure is equal to the product. Because, well, the smallest covering is given by, well, or you can repeat this computation. In any case, you cannot have less than the product. Okay, and now we ask, now the following theorem, which is Fubini. There are two theorems. The first one tells you that if a function is integrable, be careful, not measurable, integrable in the product measure, so now we have this product measure, mi, which is mi star, mi cross ni, is mi cross ni star restricted to the measurable sets. Let's say omega is the measurable set. And this omega contains all rectangles. Okay, so the measure is defined. So the first tells you that if you know that the function is integrable, so its integral in modulus is finite, then you can compute by the repeated integral formula. The second is Tonelli, which but this is not removing the problem in some sense, because still you have to prove that something is integrable, so the integral is finite. So the second theorem is Tonelli, which tells you that if the repeated integral is finite and the function is positive, then the function is integrable, and the integral are the same. So at the end, usually you say just Fubini Tonelli, and just remember that basically you can always integrate iteratively. So the Fubini set, let's f be mi star ni integrable, which means that the integral modulus of f mi ni is less than plus infinity. Then, and assume, okay, there is a problem with the zero sets. Because in the way I give you the statement, for example, this can be, so let's say both are the Lebesgue measure and A and B are Borel, are the Borel sets. In the construction here, what I get is a measure defined on the completion of the Borel sets. Because it's the way that I construct it, I get a measure, then the set of measures 0 are measurable, and hence is the Borel set plus the set of measures 0. So I cannot expect that a function which is measurable here will be measurable, for example, in one of those. Simply because I give you a set of two sets of measure 0, I take the product, and I get that it is a rectangle. It is a rectangle, but I cannot compute these values just because I forgot to complete the algebra. Okay, this is, so let's assume, so for example, I take we know that in every set of measure 0 which is uncountable, you have a non-Borel subset. Well, we did the example with the Vitalik function. No, you remember the Vitalik function, which maps set of measures a set of positive measures. Then there is a non-measurable set there. I just push back. The Vitalik function is B continuous, so you get a Borel set. And well, I have this trouble. It's just that to every subset of Borel set of measure 0, I give the measure to be 0 and I say they are measurable, but they are not Borel. So, if n is not in the Borel set of R and the Lebesgue measure of n is equal to 0, then, so the Lebesgue to measure, as I built here, of n times n is equal to 0. Is a rectangle and is the product of 0 times 0. I just used the definition. But if I forgot here to put this to be the complete sigma algebras, well, what I said is not correct because I cannot compute by the product. But n, so clearly n does not belong to Borel, so but if I forgot to complete the Borel with respect to the one measure, then okay, I cannot compute L1 of n times L1 Ln. So actually the formula for the rectangle cannot be computed. But clearly still you get that this function, this measure is complete because of the difficult deconstruction. But you cannot compute by iterating the integrals in some sense. You cannot use a simple formula. You have to say that, well, I can approximate from outside with Borel set of measure 0, but with a Borel set of measure 0, but I cannot say that. Well, I cannot write the formula in some sense. So here a basic assumption is that Ni is complete. And now the question will be why I just assume the second one to be complete. Then, so the statement, then for all let's say, for the first component almost everywhere x, f, so y maps to x, f, y is Ni integrable. So now this is, I fix x, so it's just a function of y. X maps to the integral of f x y Ni dy. So since it's integral, I can compute for almost every x this function. And this happen to be is Mi integrable. Okay, this statement forget, and then you have just to read what I wrote down. And the integral of f Mi times Ni is equal to the integral. First you integrate in y, and then you integrate in x. Okay, so this sentence is just to say that the formula here is meaningful, because this is by this assumption. Then I read the right hand side, and then I discover, first I'm integrating in y, so this function should be defined as a function of y for, well, since I need just almost every x, for almost every x. And now once this function is defined for every y, I can integrate, so I have to assume the integrability, and this as a function of x should be integrable with respect to me. So now the question is why just D is complete?
I mean, this is over not any measurable set in product. This is on the set of the form AI times BI.
Which
A
one?
times
Which?
the integral.
This one?
No, the first one, I mean. Yeah, this one. Is over a set of the form
One.
A times B.
One.
If it's not A times B, what are the for example, what is it?
X times Y.
Yeah, but not
The whole
over any
space.
subset of X times Y.
Why?
Measurable subset of X times
But
Y.
why do you see any restriction? It's F.
No. I mean, for example, we have the integral of a function or in respect of the product measure, but over a subset which cannot be expressed in form of product.
Yeah.
Then I cannot apply this.
Why? Yes, you can.
No. If it's a subset of X times Y,
So
of the form A times B.
let's move on this side.
Yeah.
So how to compute the area of a circle?
Well, I know, but not that way.
No, but you use a fixed x, then its length is 2 times 1 minus x squared.
Yes.
So I integrate. So this is what? This is the integral from, this is the integral from the characteristic function of the circle, the ball, of radius 1 in R2 around 0 as a function of x, y. I integrate in dy, and then I integrate from minus 1 in dx.
Yeah, but what's the set that we are integrating over it? What's the subset of R2 that we are integrating on it?
There is no, I'm integrating the whole space. I just define that the function
Yeah, that's
f is the characteristic function of the ball, of the unit ball.
Yeah, that's what it is.
And so I don't see why I need to put anything here. If I know that here it works, it should work also there.
Now, when in the beginning when we define the integral of Lebesgue over R, we can integrate over any measurable subset of R also.
Yes, but also on R.
Yes. So here we define it on the whole space.
Yes.
And it's okay. But now when we want to pass to subsets of this whole
I put
space,
just the characteristic function, so the integral of A of f is equal to the integral f of A, and then it's still a measurable function. Otherwise, it would be a little bit less useful. Okay, so essentially, this sentence here is just to give meaning here. Okay. So my origin, you know the answer.
I guess, okay, we can notice that the product measure is complete first of all because it's the outer measure.
That's complete, yes.
And if V is complete, then whatever we take a non-Borel set, negligible set,
But
the product will
Yeah, okay. But why only me and not me? Why just the second and not the first?
because we need for almost every x to have this integrable, so we need at least that we can compute the integral if it is a characteristic function.
Yeah, exactly. Like here, no? You take n. So essentially, if you add a set which is negligible with respect to mi star and it's a product set. Okay, so this integral essentially tells you is contained in a larger Borel set in our example. So you're okay. So a function which is so this mi almost everywhere essentially says that the function is you're integrating in the complete sigma algebra. While I can remove just a set of measure 0, but I have to be sure that this is integrable. So the thing is that if you take n, which is one of these bad sets, times a, whatever it's a, so you see, I can just remove a set of measure 0, but at the end I'm always integrating with respect to n. So the statement is asymmetric simply because I'm writing this formula is asymmetric. So I'm not saying, so the remark is that I'm not saying that f mi times ni is equal to the integral with respect to mi, and then the integral in ni. You see? Just the statement is asymmetric and the assumptions are asymmetric. If I want to set this equality, I have to say that I exchange the roles. So mi is always is complete, and then I have the equality. Okay? So let's see the proof. It is never happened. You always take complete sigma algebras, and then you have the. It's just interesting. We cancel and sketch of the proof. Sketch of the proof is okay. Is the standard reduction argument. At the end, we arrive to just one case. And then we discover why we need the integrability. Okay. So I'm saying that what you do is just basically you take the definition of integral, and so you discover that you don't need to prove for a general f, but just for like that.
Integrable?
Integral, yes, but not for general integrable, but for how do you compute the integral? By simple function. By just simple functions. Because I know that there exists a sequence which is increasing or decreasing, so I can split it into two parts. So if this holds for the positive and the negative, I'm okay. So f positive, so I can take something increasing. Increasing, the monotonicity is okay. So because this is the sloppy part. If there is a function which is increasing, so here I pass to the limit. This is increasing, so I can pass to the limit. So this is increasing as an integral because the function is increasing, so I can pass to the limit here. This is increasing, I can pass to the limit there. Okay, so simple function. Then simple function, then I can still reduce to characteristic functions. So just characteristic function. This is a big simplification. Well, and now I have just to use the definition. So if you give me a set E, so mi of E, well, is for mi star, so this is the infimum, the sum AI di. Okay? So we need to prove that, so essentially what I have to prove, this is the infimum. So now instead of having something increasing, I have something which is decreasing. Because, so this is something like a simple function, which is, so this is a simple function. Semi-simple, let's say, because I have counted many function of the form is the sum of the characteristic function AI times BI. Okay, and then assuming that this thing is shrinking, I'm saying that okay, this guy is shrinking. Okay, and then I say, yes, that's why I need integrability. Because here I have something which is decreasing, and here I do the same, it's something which is decreasing, but which was the fundamental assumption to when you take a monotone decreasing sequence of positive functions?
At least one setup.
Yes. And what shows that this happened? being integrable, the level set are a finite measure. So we are sure that at least one of these will be finite, otherwise its measure is infinite. Okay, so the basic assumption is that this guy is less than plus infinity. And so I use the same for monotonicity. So essentially, now I have this sequence of functions which converges to the characteristic function, monotonically decreasing, and I need to pass to the limit. So essentially, I need to prove the end just for this function here, because I can apply monotonicity. Understand what I did twice the monotonicity. The first is that I have a sequence of increasing sequence of simple functions. No problem, I can always pass to the limit. I have no assumption of decrease. Well, first of all, to zero is that I notice that being integrable, I can just take the positive and the negative part. For positive, I have a sequence which increase, no problem. The monotonicity has no assumption. Now I take, so I reduce to essentially simple function of this form which converge, they decrease to the characteristic function of my set E. Okay? I want to use monotonicity, I need to be sure that at least one of those is a finite integral. Well, I'm fine because my assumption tells you that this guy is finite. Okay, this is a little bit sloppy part, but now we arrive essentially to I need just to prove for a very simple case, which is that sum. So I have the integral of the sum of characteristic functions integrated in mi plus ni. Okay, let's compute it. Countable sum, well, it's a sum of positive functions, so I can put it outside, again by the monotone convergence theorem. And now this is the mi. Okay, that's it. So in order, now I cancel because this has not this shape yet, no? So now I want to rewrite in this form. So let's compute the other. The integral of the sum of characteristic function. This is a function of xy. I integrate in mi dy, and then I integrate in mi dx. It's okay. So now for every x, so I can define the function, so for every x, so that is an exercise, I get lost indeed. For every x, I have the function which is the sum, a characteristic function. I don't know if I really need it, but okay. Do I need it? I think no. I think I don't need it. It is already is trivial here. Because again, I can say that this guy I put outside because again of monotonicity. So sum over I, the integral of PAI times PI xy mi dx mi dy dy dx. So here I use the completeness. Okay, equal to. Now this guy over here I can put it outside. So it's the sum over I, the integral PAI times PI xy mi dy mi dx. to be sure, I'm not using here a complete, I'm using the previous step when I use the monotonicity. Okay, but now this is as a function of y, this is equal to the measure of bi only in the set ai. So this is equal to the sum over I, the integral. Now, only in the set ai, otherwise it is 0, is ni of bi. And so, finally, I'm defined, this is the sum which is equal. So the completeness, enters when I take the limits. Because when I take the limit, so I need to prove that it converges to 0, but this converges to 0, well, so I cannot say that it converges to 0. So it may so because the convergence to 0 is for the measure mi times ni. And then when I do the same formula, I say that it may converge to, well, so the problem is the following, that we do the complete sigma algebra. Well, if I do the algebra generated by the product sets, I get something, and in the Fubini theorem, I do not need to assume that mi is complete. Then, okay, but in the case, it's the passage to the limit, so the completeness is for the passage to the limit. Well, actually, it's not yet for the passage to the limit, because the completeness in this proof does not appear. The completeness is really at the beginning. Because the approximations converge to f mi cross ni almost everywhere. And still is not here. Gosh. Because you see, now it is here, because you see the infimum that I'm using for f does not converge really to this guy. This is almost everywhere. So the completeness is in that step. Just because the limit, so this is a little bit subtle, I'm sorry. But so the limit of the approximations is an f tilde such that f minus f tilde, the integral, is equal to 0. So the approximation we build is something that has the same, they differ only on set of measures 0. And then when I apply the iterated formula, I discover that this set of measures 0 can be integrated or not. It is can be certainly integrated when I assume the measure is complete. And the remark indeed is the following. The sigma algebra of generated by rectangles is a very delicate thing that does not need the ni completeness. So, okay, but you can. This is not going to be asked. It's just for your knowledge. So the completeness is exactly because I construct the product measure in some way. Otherwise, I could always restrict to the sigma algebra generated by rectangles. In that case, I don't need the assumption on Fubini. But okay, it's a detail because you take everything complete. It never happened to me that I don't need something which is not complete. And I think in 20 years it means that it's really something. You can just put when you need. Okay, so far so good. So we have that if a function is measurable in the is integrable in the product, I can compute the integrals. So now the second, the Tonelli tells you how to compute it is integrable.
A question, I just want to know if I'm right, but I think we can use also the completeness to prove directly that nu almost everywhere the map from y to f of xy is integrable, because we have seen in previous lecture that if a function is L1, then the outer measure of when the function gives infinity is a 0.
Yep.
So if the measure mu is complete, then mu almost everywhere we should have
the second measure is complete, or the first?
the second
The second.
is complete. No, it doesn't work. It's just a mu star.
The first you don't need because you say that you just remove a set of measures here. It's in the statement. In the second is that it is exactly that example, no? N, so a non-measurable set for Lebesgue times an interval. This is set does not belong to the sigma generated by rectangles. Because you get some larger set, a Borel set, which is still of measure 0, but it contains your non-Borel set. It's exactly this fact. So when so the limit you build here, since it's done by using Borel sets, it's a function which is still Borel. And then you are fine. So if I say, let's assume f to be Borel and integrable, I don't need the assumption of completeness in the statement. It's just because exactly I have this trouble that the way I build the product measure as all contains the sigma, all these sets, which, so when I rewrite the formula, I discover that actually I have that my f tilde, which is the limit of my approximation, differs on set of measure 0 here. So when a set of measure 0 has measure 0 and the formula is meaningful, well, I just look at the example, I need the completeness. Because I should say it is a subset, so for almost every x, this section is a subset of measure 0. This is for free. So I have to say that its measure is 0, well, I have to say that the measure is complete. It's a little bit like, just for coherence. At the end, nothing changes. Nothing changes. It's just coherence of the formula would be meaningless because the integral of f is not defined if f is not Borel. And while the integral in the product is defined even if f is not Borel. Just this. You can say, I take a Borel function and I let them equal. And then it is the first approach. The second, I complete on the other side in order to give meaning also to the other case. I'm sorry, it's just, it's not, this lesson is it's just how to say, additional material, but the two formulas that you need to know. But these are additional materials that I hope you like, because it is interesting. Are these details? But clearly, when you need them, you can always look at them. But at least you know that there are some details. It's not really straightforward if you want to make the thing coherent. Okay, so now the second theorem is Tonelli. It is the last. No, we need to do another thing. But then you will have fun. Oh, we have fun. Tonelli, and Tonelli says that, let me state that correctly. Now you don't know that something is integrable. Okay? Because this is what you want to prove. But so how to be sure that in any case I have something which is finite, or sigma finite. Because if I do, if for any finite set I do the limit, I can take the union, and then it's fine, because the integral is. So I need to assume that x and y are sigma finite. So essentially something like, say, they are finite. Again, I need the knee complete for the same reason as before. And I take f greater or equal than 0, which will be the modulus when I have to estimate the integrability. And the measurable in the product. Then, the result is always the same. Then, what I say, then fx, depending on y, is knee integrable, knee measurable for me almost everywhere, almost every x. And then I have that the integral f as a function of x is measurable, is mean measurable, and finally the equality holds. So essentially here, I'm not saying that the function is integrable here, just is measurable, but I assume that the functions are sigma finite, the spaces are sigma finite. Then let me just say what is the basic. So the construction is the same. Is the same. The only thing is that I need to prove that, well, you remember there was a step where I have the outer approximation, and then I have to let this converge down. So I can do either if I know that this is finite, because the function is integrable, or because the measures have finite space. So the proof, the only point, partition, x is the union of some xi, y is the union of some yj, and xi, mu yj are less than plus infinity. And now the point in the proof where I have to assume that at least one has finite measure is trivial, simply because the spaces are finite measure. So now the formula will be the integral of f is the sum yj xi times yj f. And so you need just to prove here. No? This holds by definition, by monotonicity, because it's still the union. And I need to prove only the formula in this step. Okay, sorry, this is a sketch, but I want to tell you about Hausdorff measures. So essentially, let me repeat how to prove it, how you use the theorems. I give you a function, and this is a standard assumption. You cannot get rid of it. And okay, the completeness is for free. And then, okay, you estimate this integral here, which usually is easier to estimate than this guy. If this is less than plus infinity, this is less than plus infinity. And then, this holds only for positive functions. Once you know that the integral of the modulus is less than plus infinity, you can use Fubini, that tells you that also the integral for L1, for the L1 function is equal. Okay, so, well, this can be also plus infinity in this theorem. So it just tells you that it's less than plus infinity. So how to use it? Essentially, f is measurable. You Tonelli estimate the integral of the modulus of f by this formula, and then you apply Fubini. Integral of f is equal to the integral. Okay? usually, you see, the real is slightly different. The difference is that here is just measurable, the other is integrable. Usually you say just the theorem for Bianchini. Okay, so let's have some fun now. This is not going to be asked, but I think is interesting. So it's the definition of how those measure and dimensions. There are 2 points, still one. Because these measures are quite important, and we don't see anything. So how's those measures? So the observation is the following. I'm not going to prove this observation. Observation is the following. Essentially, if I give you a set E, okay, and okay, then for all epsilon, there exists let's say, if this compact, let's say, a countable number of balls, be centered in xi of radius xi in Rd, disjoint, such that the measure, the Lebesgue measure of E minus the union of these balls is equal to 0, and the Lebesgue measure of the ball, the union of the ball minus the set is is less than epsilon. So I can choose the covering as much as I want. Well, we have that thing was, if you remember, was the Vitalik theorem. We have the Vitalik theorem in 1D where you use intervals, and the general case is some covering like the Bezikovich theorem. This is the Bezikovich theorem, more or less. And essentially it tells you that the balls can be used to cover basically almost all set, and you don't waste too much. You don't need too much more space than your set. Okay, so essentially when you take the infimum among the coverings, you get the Lebesgue measure of the set. Okay, so the covering, the measure of the ball is Ri to the d times, okay, this times the measure of the unit ball, no? So instead of taking R to the d, let's take another measure. So define now for any set A is the infimum sum. Now this omega k is the Lebesgue measure, LK measure of the ball in Rk of radius 1. It's just a normalization. And I put R to the k, sorry, the diameter of the set E I to the k. Sorry, this is a radius then 2, radius 1, yes. No, if I put the diameter is radius, it should be divided by 2 to the minus k. Because it should be the ball, so it should be 2. Yeah. And now, sorry, 1/2. 1/2. That's all. And A is contained in the union of the sets. So essentially, I give you a set. And the diameter of EI is less than delta. So you have to choose balls or sets, whatever, whose diameter is less than delta in order to cover all, and then you add up with this diameter of K. So the properties are the following. Well, this is an outer measure because it is the infimum. When delta goes to 0, I have less sets, so it is an increasing function. So it's decreasing then. And so I define the Hausdorff measure, the Hausdorff should be outer measure because I'm saying for any set, is equal to the lim for delta which tends to 0 of the approximated Hausdorff k-dimensional delta measures.
The omega k are given function.
Is a given constant.
Ah, constant.
Is a constant. Is the measure of the unit ball of radius of diameter 1. It's just normalization. You can remove it, but it's just in order to have the same Lebesgue estimate. Okay. This satisfies Kara-Theodori condition because you see, for any, since being the limit when delta goes to 0, the diameter of the covering converges to 0. So when the diameter is less than the distance of two sets, the two coverings are disjoint. So HK is a Borel measure because of Kara-Theodori. The other thing is that HD is equal to Lebesgue because of the covering of the estimate above. The infimum of the covering, well, it tells you, really the covering integral tells you that that essentially is one covering like this one. And then another property is the following. So what is the relation? Okay, when something bad happened, that HK is not sigma compact, sigma finite in RD when K is less than D. And indeed, usually, you take HK restricted to a set of finite or sigma finite measures. Some set E is sigma finite. You do not express properties for non-sigma finite measures because they are bad in general. And now the other thing is you want to see the dependence with respect to K. So this is, it gives you, so an example, so let me say, as an example for you is that HK restricted to a plane, let's say plane of dimension K is equal to the LK on the plane. So if you have some smooth surface, is essentially like the the push forward to the smooth maps of the measure of the dimension. So it is the nice generalization. And now let's discuss still one thing. This is not, it's just for knowledge. I'm prefer to waste some time for this important argument. So the dependence with respect to K. So let's look at the definition. HK plus delta, let's say HK plus epsilon, delta of A. Okay, you take the infimum, and now here you have K plus epsilon, but K plus epsilon is a delta, is at most delta. So if you take the covering with, so you have that this guy is less or equal than, okay. So let me think, if I take the optimal covering with is larger, sorry, than delta. So if I take the optimal for K, K plus I take the optimal, and then this is epsilon, so it is larger or equal than delta to the epsilon. No, it's the opposite. It's less or equal than delta to the epsilon h k delta of a delta. So let me think. Yes. Because here I would say I would have k plus epsilon. And then I put the delta as bounded by delta, I put it outside and then have a covering. So when I pass to the limit, I say I'll take that h. So when I pass to the limit, what happens? So if hk delta of a is greater than 0, then hk plus epsilon of a is equal to 0. Vice versa, if hk plus epsilon of a is greater than 0, then hk of a is equal to plus infinity. So what I say is the following property. There exists a unique k-bar, which is called the Hausdorff dimension of A, such that hk of A is equal to plus infinity, k less than k bar, 0, k greater than k bar. And for k greater than k bar, you don't know. In particular, for example, if you take a plane of dimension k and you compute the Hausdorff dimension, you obtain exactly k. Take any smooth surface of dimension k, you obtain that its Hausdorff dimension is exactly k. But you have also sets which are non-smooth, where you can in any case associate the dimension. So this dimension, is not a classical dimension. It's just tells you some dimensional information. No? What is the enlargement in how you rescale? You rescale like the dimension k, more or less, you can say. Okay, and last thing that I want to discuss with you.
A question.
Yeah.
The first condition, isn't it hk of a finite?
Here.
Yes. Because
Yeah, it's finite. Yeah. Otherwise, you know. Okay, the last part is a Lebesgue point. Is the only important argument we leave outside. So a Lebesgue point of a function, so if f is integrable, then x is Lebesgue point. If these are in RD, well, it doesn't need. Let's say in RD, because if the limit when r tends to 0, 1 over the Lebesgue measure of the ball, that's centered in 0 of radius r, the integral in the ball centered in x of radius r of f1 dy, so it's the average. You are integrating around x and you take the average. And the limit existing is equal to f of x. It's something like a continuity point. From the point of view of the measure, it tells you that it is a continuity point when you remove a set which becomes negligible. And now the fundamental theorem, which is a theorem of Lebesgue. So under these assumptions, almost everywhere x is a vector. So when you take the average around almost every point and then you rescale it, so you divide it by the measure, which is the average. Okay, so the limit is equal to the function. And I have no time even to prove it. So the proof is in the same way we use random-Nikodym. Because the set for which this limit is less than f, or that lim sup is less than f, it means that every point has a ball whose average is less than f. And now you use the covering, and you discover that its integral is less than f, which is a contradiction. And the same when you assume from above. So it's like for random-Nikodym, essentially you can construct the limit f by considering the points where its average is less or larger, or the limits that are less or larger than the function. They cannot exist. Okay, we stop here. So Thursday we do some exercise. Tomorrow you have the tutorial, if I'm not fine, and that's it. The tutorial is tomorrow. No?
Yeah.
And so we do even Thursday some exercise, and we stop here. This part, but Fubini and Tonelli. The other part is not. Even maybe you find some exercise, but they are not. I will not ask. This part is not. It's for your knowledge. And Fubini and Tonelli, I just need that you know how to apply them, and was that arrow that by Tonelli you get the integrability, and then you use Fubini to get the equality. That's it.
The schedule, the tutorial is in Thursday. The tutorial
is on Thursday.
Thursday.
The tutorial.
Yeah.
Okay, so we do two exercise sessions on Thursday.
Okay.
I'm not adding any. Well, we can see the proof, but I think it is enough.
So the last lecture will be a tutorial.